All right, so what I'm going to do is explain to you, we're on page 68 of your workbook, electromagnetic radiation, because that's the first thing we're going to be looking at in this unit. Now, electromagnetic radiation may seem like a term that you've never experienced. It seems kind of abstract, but in fact, electromagnetic radiation is just a kind of radiation, or a form of radiation, that includes, I'm going to show these to you below and not write them. Radio waves, when you are jamming out in your car, that is thanks to electromagnetic radiation. Microwaves, when you are chowing down on popcorn, that's thanks to electromagnetic radiation. Infrared, visible light, all of these gorgeous colors, that's thanks to electromagnetic radiation. UV radiation, if you've ever gotten sunburned, that's because of electromagnetic radiation. X-rays, if you've ever broken a bone, you've had to get x-rays taken. And then also gamma rays. And so we're going to look at how these different types of electromagnetic radiation differ in just a second. But the first thing that I'm going to do is actually give you a second definition. And that second definition is that electromagnetic radiation is the flow of energy and the most important thing for us to remember, and we're going to come back and address this in just a second, is that all of the energy is moving at the same speed, and it's moving at the speed of light. Moving at the speed of light. We're going to see how that impacts us in just a minute. All right, so how I'm going to start this off, I'm going to have you note a couple of things, and then I'm going to give you a couple of definitions, and then we're going to look at a quick simulation. So the first thing I want you to notice, if you can imagine this being a slinky, and imagine you're waving the slinky so that you get these waves produced. If you notice, if you're waving it really, really loosely, not with a lot of energy, you would create waves that kind of look like these. And I'm going to define a couple properties of these waves, but this is a low energy wave. Now, if you notice, if you start to shake it a lot harder, and you impart more energy, this is what the waves would look like. So that's one factor we're going to be looking at, the energy of the wave. All right. The next thing that we're going to be looking at is two other properties that we can define to describe the wave. And the first property that we're going to be looking at is wavelength. Now, wavelength is the distance between a crest of one wave to the crest of the other. So I'm actually going to scroll down for a second, and I'll write that definition for you guys in just 1 second. Okay. All right. So your wavelength is the distance between the crest of one wave and the crest of another. All right. Now, there's one more thing that I'm going to add in a second, but I want you to see this first to understand what I'm about to tell you. So the wavelength, if I look at these two different waves right here, I've got a crest right here, that's the top part of a wave, and I've got the crest of another wave right here. And so this distance, if I were to measure it, that would be my wavelength. If you notice, this distance is the same if I find the distance between two crests, or if I find the distance between two troughs. The troughs are the lowest part of the wave. Okay, so those two distances are the same. And so what I'm going to do is I'm going to add to this definition we have, and I'm going to say or trough. And here I'm going to say or trough as well. Okay. Now a couple of other pieces of information for you about wavelength. We represent wavelength with the symbol lambda, and it looks like that. That is lambda. So if you see that, which you will see in formulas and equations in just one sec, that represents wavelength, the distance between two crests of different waves or two troughs of two adjacent waves. The other term that I'm going to introduce is frequency. Now, frequency, when you think about the term frequency, you think about how frequently something is happening, how often. And so the frequency, the definition is it is the number of times the crest of a wave pass a point in 1 second. So, how frequently a crest will pass a given point in a given amount of time in 1 second, right? I'm going to show it to you in 1 second actually with the simulation, but the important thing for you to know is that the units for frequency are either seconds to the -1, because it's saying how many times a crest will pass in 1 second, or the other unit that's used is hertz. The last thing is that the unit for frequency, while the unit for wavelength is lambda, the unit for frequency is this V looking thing, and it is called nu. All right. Now I'm going to show you quickly a simulation for us to understand the relationship between wavelength and frequency, because the key thing for you to remember here is that your speed of the wave stays the same. So we're going to see how that affects your wavelength. So we've got this right here. Okay. Now I'm going to start off this wave. Okay. And we're going to have it go pretty dang fast. I'm going to decrease its size for you. Okay. And so what I want you to see is, after it gets going a little bit, just how frequently a crest will pass. So the amount of time it takes for the crest to pass. So the frequency is defined as the number of crests that pass in 1 second. So obviously this is not going super fast. Obviously it goes much quicker than this because it's counting the number of crests. So one crest, another crest, another crest that pass in just 1 second. So obviously this is pretty dang slow. Now notice the distance between the crests. That is your wavelength. And so kind of keep in mind what your wavelength looks like. What I'm going to do now is decrease the frequency. So decrease the number of crests that pass this point in 1 second. So if you'll look, okay, I'm going to actually increase it just a little bit for you to be able to see it. So we're going to let it balance out. Okay, we've got one crest, another crest, another crest. Okay, so the frequency has decreased. The number of crests that pass a given point in 1 second has decreased. The other thing that's happened, notice what's happened to the wavelength. Okay, think about what's happened between when it looks like this and when it looks, hold on, give it a sec, when it looks like this. Notice that the wavelength has decreased when the frequency increased. And so what we'll say, I'm going to quit this really quickly. What we'll say is that wavelength and frequency, these two guys right here, are inversely related. Meaning, when your frequency increases, like what you saw in your simulation, your wavelength is low. When your frequency is high, your wavelength is low. If your frequency decreases, like what we saw in the simulation, then your wavelength will increase. All right? The last thing, as always in chemistry, we're now going to put this into mathematical terms. Now, as we'd said before, Electromagnetic radiation, all types of electromagnetic radiation, move at the same speed, and they move at the speed of light. So, the formula for determining, for relating frequency and wavelength is C, which I'll explain in a sec, equals lambda, remember that's wavelength, times frequency. Okay? Now, your C, in this case, is your speed of light. Because all types of electromagnetic radiation have the same speed of their waves. Okay, they're all traveling at the same speed. Now that speed, I'm going to give it a number now. It is 3.0 times 10 to the 8th meters per second. Now that gets you thinking, oh my goodness, what are the units for wavelength and what are the units for frequency? And so the units for wavelength are meters. The units for frequency, there are two different units that can be used. We'd already gone over this, seconds to the -1 or hertz. Now, of course, we can alter these units, by adding a prefix, whatever, but the most important thing for you to realize is that the speed of light, the units for the speed of light are meters per second, which means that the units for wavelength need to be meters, the units for frequency need to be seconds to the -1, or 1 over seconds, which is the same thing as saying hertz. So what I'm going to do right now is I'm going to do this one example problem, and then I'm going to call it a day. So in this problem it says, what is the wavelength if the frequency is 1 times 10 to the 14th seconds to the -1? So that's my frequency. Okay, that's my nu. So I'm going to plug it into my formula, C equals lambda nu. Now I know my speed of light, it's 3.0 times 10 to the 8th meters per second. I'm trying to solve for my wavelength, so I'm going to put lambda right there. Now I'm going to multiply this by 1 times 10 to the 14th seconds to the -1. And so in order to solve this, I need to isolate my lambda. And so what I'm going to do is I'm going to divide both sides by 1 times 10 to the 14th seconds to the -1. I'm being consistent with units. If the units confuse you as you're working, as long as you're clear on your units when you finish, I'm fine with whatever you need to do. Okay? Now, since this is 1 over seconds right here, and this is 1 over seconds right here, these two will cancel. And so you end up with units for wavelength, actually what you expected, meters. And when I divide in my calculator, I get 3.0. But actually, if you notice, this is only one significant figure. This is two significant figures. So I'm going to keep it at one sig fig. So 3 times 10 to the -6, and my units are meters. Okay, so that is the wavelength that I just calculated. What I need you to do right now is on your own. You can rewatch this video if you need to, or if you've got it, awesome. I need you to complete number 1 and number 2 for class. And we will start class with a quiz on a problem that looks just like these guys. All right? And that's all there is.